Hello everyone. So we are going to start the last part of the distillation. So this is the part 7. So here we are going to discuss some of the left out instrumentation that are involved in the process of distillation in pharmaceutical operation. So without wasting any time, let's start the presentation. So you see, the first thing it is the fractionating column. So we have already discussed in our previous presentation regarding the fractional distillation, right? So in the fractional distillation, we need to have the fractionating column. So how these are used? Actually, you see, in fractionation, we know that in fractional distillation, special type of steel heads are required, right? So that the condensation as well as the re-evaporations are affected continuously. So if we just recapitulate the thing we have discussed in the previous presentation in the part 6, where we have discussed how the liquid it first get vaporized, again it get condensed, again it get vaporized, so that we can separate out the mixture of the components based on their difference in the boiling point. So if you remember that this type of distillation, this is known as the fractional distillation. So fractionating columns are used in the fractional distillation. So fractionating column actually it helps in the process of condensation as well as the re-evaporation, right? So these columns are also known as the fractionating column, as I have already told you. So a fractionating column, it is essentially, it is a very long tube where the vapor it passes upward from the steel, right? From the steel the vapor it passes upward and it get partially condensed, right? And this condensate they flow down the column and it again come back to the steel, or you can say flask, right? So the columns they are constructed with the following speculations to give the advantages. So what are the advantages? Number one, it offers a large, these columns they offer a large cooling surface for the vapor to condense. Number one. The second advantage is that an obstruction to the ascending vapor allows easy condensation. An obstruction to the ascending vapors. Now the vapors they will ascend from the steel or the flask. Thus a obstruction from the ascending vapors it allows easy condensation. So the fractionating column types, basically we have two types of column. Number one, it is the packed column. Next, it is the plate column. So let's discuss how it works. The first one, it is the packed column. You see, some form of the packing they use in the column to affect necessary liquid and vapor contact. This packed column, they make the contact between the liquid and vapor. And this packing it is generally made up of, or it has the single turn helices, which are also known as the spirals of wire, of glasses, glass rings, cylindrical glass beads, etc. Right, now construction, how the packed columns are made. The packed column it consists of a tower. Tower means just like a vessel, a long standing vessel, right? Vessel, or you can say a burette like structure. The packed column it consists of a tower containing a packing that becomes weighted. When it becomes weight with a film of liquid which is brought in contact with the vapor in the intervening spaces, means that this packed column, when it is placed above the steel, it first of all get weighted by the virtue of the ascending vapors from the flask or from the steel, right? So a long fractionating column is necessary. You just remember this thing. A long fractionating column is necessary when boiling point of the constituents are close together, fairly close. Suppose the boiling point of the constituent 1, suppose there are 3 constituents A, B, C. A boiling point is 60, B boiling point is 65, C boiling point is 70. right? In such cases, you need a long fractionating column because the boiling point they are close. We have just 5-degree differences, right? But you can use a short fractionating column when the boiling point are very different. Suppose we have A, B, C, right? 3 components. Now the boiling point of A is 50. The boiling point of B is 100. The boiling point of C is 150. In such cases, you can have or you can use a short fractionating column. Application, basically you see the packing must be uniform so as to obtain a proper channel. So if the packing is irregular, if we do the packing irregular in this fractionating column, the mass transfer becomes very less effective, or sometimes it may not work. Now the fractionating column type, it is the first one, it is a packed column. You see these are the example. This is the pear shaped packed column, right? And this is the generally rod and under disc type of column. Now in the plate column, actually you see many forms of plate are used in the distillation using the different columns. So these plates can be divided basically in the 2 types. Number 1, it is the bubble cap plates, and number 2, it is the turbo grid plates. So number 1, it is the bubble cap plates, plate type. Number 1, it is the bubble cap plate. Number 2, it is the turbo grid plates. So bubble cap column, it is used in the large distillation plants, and it is described below. You just see the construction. So the column, it consists of number of the plates mounted one above the other, right? So the caps are present on each of the plates, which allow the vapor to escape by the bubbling through the liquid. I will show you how it works. So just let us just consider the working. Here I have named the plate A, B, C in the ascending order, and the diagram it is in the second slide. I'll just go through what is it is how it works. You see the ascending vapors. Ascending vapors means the vapor which is coming out from the liquid which is present in the still. So the ascending vapor from the still, it passes through the bubble cap on the plate A. It is the first plate, right? And the rising vapor will be richer in more volatile component, right? So whatever less volatile are there, they will settle in the plate A. Means less volatile will settle in the plate A. More volatile will leave out the plate A. It will reach the plate B. First we will get plate A, then plate B, then plate C, like that. So this vapor passes through the liquid on the plate B, and they partially get condensed. Means less volatile will get condensed in A. The next part of the liquid which is more volatile than the part A, but it is less volatile than the part C, it will get condensed in the B, right? And similarly everywhere it takes place. So each bubble cap plate has the same effect as a separate still. I will show you how it works. Just see A, B, C, D, E, right, in this type, right, in this type. So if we connect this, right, the more volatile will reach here, highest volatile. The next highest volatile will reach here, the next volatile will reach here, somewhat like that, and the less volatile will be collected here, right? So this is the arrangement actually. You see liquid from the plate above from the above plate, it will reach here, and this structure is present in each of the plate. So suppose the condensate from here, it will reach here through this. So this is, you see, liquid from the plate above here, it will reach here, again it will go down, right? So now the thing is that the plate columns, or you can say bubble cap. So advantage, what is the advantage? The bubble cap plate, it is effective over a wide range of vapor liquid proportion. Thus there is an excellent contact as the vapor bubbles it pass through the liquid. This is the first advantage. But there are also some disadvantages, like a layer of the liquid on each of the plates results in considerable holding or hold up of the liquids over the entire column. So the liquid may be held up at a particular portion for the entire column. This sometimes leads to the overheating actually. So the need to force the vapor out of the caps, because as the vapor or the liquid may remain there, or the vapor may remain in the partitioning area, so we need to force it out through the liquid and lead to a large pressure drop in the column. We know that when we are going to apply force over the vapor will go out, but there will be a pressure difference or pressure drop. The column, it does not drain when it is not in use. And the structure, it is very complicated, making the construction and maintenance very expensive. The next, it is the bubble cap. You see, these are the bubble cap. These are the bubble cap. So the liquid from the upper portion or upper part, suppose here it is C. The condensate from the C, it will reach here, it will get again evaporated from here. Again, the remaining liquid, it will come here. Suppose this is the C, this is B, this is A. From A again, it will go down to the main flask. So A, B, C, or suppose A, B, C, in this way it is actually arranged. So the theory of fractional distillation is simple. That the fractional distillation, it is suitable for a system when the boiling point of the mixture is always intermediate between those of the pure component. I will explain is, just see, the fractional distillation, it is suitable for a system. In what type of system? For a mixture. Actually, when the boiling point of the mixture, suppose A and B are added, right? The boiling point of the AB, suppose we have added A and B, the boiling point of the mixture, it is intermediate with the pure component. Suppose A had a boiling point of 50, B has a boiling point of 100. Now if we add A with B, and if the mixture have a boiling point of 75, in such cases fractional distillation can be operated. Here, there is neither a maximum nor a minimum in the composition curve, as we have already seen this thing in the Raoult's law. So these systems, they are known as the azeotropic mixtures. Example of azeotropic mixtures are benzene with toluene, carbon tetrachloride with cyclohexane. So distillation process, again, if we see, so if you see, suppose A and B, they are added, right? Now the partial pressure, which we have already discussed, or the vapor pressure of A, it is PA and PB, it will rise until it becomes, when we heat a mixture of A and B, the pressure of the individual component A and B will rise until the pressure, it becomes equal to the external pressure. The vapor which, suppose A and B are added, the vapor which first form is always enriched with the less volatile component. Suppose we have A and B, A is more volatile, B is less volatile. If we add A and B together and if we heat it, the vapor, the first vapor which will form from this mixture AB, it will have maximum portion of the component of A, because A, it is more volatile. So here we have given, or we have taken one example. You just observe this graph. I am going to explain now. Now assume a two component mixture, suppose A and B, it is a two component mixture. So the mixture, it is composed of 30% of A is there, suppose 30 ml of A is there, 70 ml of B is there, right? Now the boiling point of the mixture is found by drawing the vertical lines from W. This is a point W. We are going to find the boiling point by drawing a vertical line where it will intersect, this vertical line where it will intersect where the lower curve, that is the X, right? Now from the X, we are going to draw a horizontal line. From the X we are going to draw a horizontal line, right, where it intersects the W, right? Now you see, from the X we have reached a point Y, right? From the Y, now we are again going to find the Y. the horizontal line it will intersect the upper curve, that is the vapor drop of a vertical line to intersect the lower axis at the point Z. So from here we are going to draw a line to the lower axis Z. Now what is this Z? The point Z, it will give you the composition of the vapor. Just see the composition in between 80 and 60. So it will give you the composition of the vapor which is in equilibrium with the composition at the W. The composition at the W, what about the composition at the W? What is the W actually? W is what? It is the composition of the liquid, I have already told you. So it will give you the vapor composition at this place, right? So lastly, you see, in the fractional distillation, we have this fraction, right? We are going to take one example. Suppose AB at a composition. AB, we have a mixture AB where AB at a composition of 5% of A, where A amount of A is 5 and B is 95, right? So suppose AB at a composition of 5% of A, it boils at a lower temperature L1, right? Now at the L1, the vapor with composition V1, here the vapor at the temperature L1, it have a composition of V1, right? It enters the column at the temperature. The vapor will now condense to a liquid composition of V1, right? Here it will liquid composition of V1, right? Now the condensate L2, here after getting condensed, the condensate L2 has a lower boiling point. You see the temperature, it is coming down, right? The temperature is coming down. Here it is increasing, right? This is the magnitude of temperature, L1, then L2. Now at the L2, what will happen? L2 has a lower boiling point and it will vaporize at a lower temperature, right? To give the vapor at a composition V2. So at the temperature L2, it will again vaporize to give a composition V2. Again, it will get condensed. It will again get vaporized at the lower temperature L3 to give a composition V3. This V3 will again condense and it will again get evaporate at a temperature L4 to give a condensate of composition V4, and similarly like that, right? So this is the way how fractional distillation it takes place. So azeotropic and extractive distillation, there are few terms that you need to know. First of all, azeotropic distillation. So it is a process. Azeotropic distillation, it is a process where the azeotropic mixture, we have already discussed the azeotropic mixture. So azeotropic mixtures, it is broken. The azeotropic mixtures, it is broken by addition of a third substance. So suppose we have two substances, we have an azeotropic mixture of substance A and B. So to break the azeotropic mixture, we can add a third substance. This is known as the azeotropic distillation, right? Which forms a new azeotrope with the one of the components. Suppose earlier we have A and B were azeotropic mixture. Now if we are adding C to break the azeotrope between A and B, now this C should have a characteristic or quality to form azeotropic mixture with either A or B. The third, or the after addition of C, the new azeotrope or composition of the new azeotrope should be AC or BC. Here the composition of the third azeotrope should be either, or new azeotrope should be AC or BC. The next one, extractive distillation. The third substance C, where we have added to the azeotropic mixture, it is relatively non-volatile liquid compared to components to be separated. In extractive distillation, for this ABC azeotropic mixture, the third substance which we have added, the C, right? The third substance added to the azeotropic mixture is relatively non-volatile liquid compared to components to be separated. What are the components you want to separate? The A and B, right? Now the azeotropic mixture, constant boiling mixture. So mixture of a special composition, suppose 5% of A, 95% of B, right? In this way we get the azeotropic mixture. So mixture of special composition giving minimum or maximum boiling Either it will have minimum boiling point or it will have maximum boiling point, then the individual component with minimum or maximum boiling point respectively. So regarding which we have already discussed. Mixture of special composition. Suppose A has a boiling point of 50 degree, B has a boiling point of 100 degree. If we mix A and B, it will form a azeotropic mixture. This azeotropic mixture will have either a maximum boiling point, suppose maximum boiling point, suppose 150 degrees centigrade, or a minimum boiling point, suppose 25 degree centigrade. That is a azeotropic mixture. So that's all from the distillation. So thank you everyone for your patience hearing. If you like the video, just press the like icon. You can share this video with your classmates and colleagues. And for further notification from this channel, do subscribe my channel. Thank you once again.